we are going to talk about the so-called LU factorization. Well, you know that numbers can be written as factored form, like if you have 15 you can write it at 3 times 5 and such. Question is if there is such a thing with respect to matrices. Well, there are plenty of them. There isn't a theorem similar to what you have seen in elementary mathematics for matrices, because there are so many ways of factoring a matrix, but there are some forms that turn out to be very useful, and we are going to talk about that. First, let me tell you, so what does L and U stand for? Factorization, it simply means we want to factor a matrix. We have a matrix A. We want to write it as a product of some other matrices. But there are so many choices here that that topic is kind of too big for us to handle. One of the choices that we have is this so-called L times U. Who is L and who is U, and why do we care about it? L stands for a lower triangular. So by now you know that we care about items below the diagonal, items above the diagonal and such. So L has an appearance of, there are stuff down here, all sorts of numbers, and stuff above the diagonal, they are all 0. So lower triangular means numbers or entries above main diagonal are 0. So an example of it would be, of course, something like 2, 3, 5, 7, 9, 11, but everybody's 0 up here. So we are insisting that top entries are 0. Similarly, we have upper triangular U. In this case, your stuff is here. They may or may not be 0, but down here, definitely everything is 0. So an example of that would be like 1, 2, 3, 0, 7, 9, 0, 0, 11. Now these upper and lower triangular matrices also get subdivided according to what is on the what is sitting on the diagonal itself. We have some finer subdivision. Unit lower triangular, we simply insist that this triangular matrix that you are working with, you have managed to make all of these diagonal entries to be 1. So this is now, they all got to be 1s here. Down here could be anything. Up here got to be 0. So this 0 simply means everything in this neighborhood is all 0. Similarly, unit upper triangular, even though we don't have much use for it in this book, that simply means you got 1s here, anything you want here, down here got to be 0. So this 0 corresponds to this. So when we are talking about having a matrix that we can break it up as L times a U, L means such a creature and U means such a creature. Okay, the matrix looking like this and another matrix looking like that. What is the significance of them? Significance is really, these are the steps that you carry out to achieve your echelon form. In the forward elimination, those are the really steps that you are taking out. They are all that data is gathered inside L, and U is what is left at the end of your forward elimination step in a Gaussian elimination. So this LU essentially captures your Gaussian elimination. We are giving some directives for what to do, etc. But if you want to just summarize all of that activity and keep the data somewhere, this is the way the data is going to be kept. All the steps in it, as well as the final product in that. So this factorization is really capturing Gaussian elimination. This is now, the steps themselves are very straightforward, and I know there isn't anything complicated about it, but the fact that it works as simple as it looks, it's a subtle argument that we try to make today, hopefully, and explain why is it that our method is going to be successful. So going down here, so our objective is given a matrix A, under certain conditions that I'm going to mention later on. We can factor A into L times U, where L, now we are going to, there are going to be many of these possibilities. To nail down just one of them, we are going to insist that our L is a unit lower triangular matrix with ones on the diagonal, where L is a unit lower triangular matrix, and U, now once we nail this guy to be having ones on its diagonal, U will become totally arbitrary. That's, we don't have any control on who's going to be sitting on its diagonal, and U is an arbitrary upper triangular matrix. Now you might come across a similar type of statement in some other book or some other course where they force both L and U to have ones on the diagonal, and they put all the non-unit entries into a third matrix. So instead of L times U, they have L times a diagonal times a U, and they break it up into three matrices. But the notation that is used in this course is L times U, and that's a more famous one. So the way I'm going to go about this is I'm going to give an example first, and then hopefully, if you have time, explaining why does it work. It's really explanation of some sort of a magical looking, if you pay attention, how come it works so easily. Now let me just refresh your memories about some of things we used to do with Gaussian elimination. We said Gaussian elimination is made out of one of three type of activities. Either you exchange two rows, or you multiply a row by a number, or you add a multiple of a row to another row. Okay, we have three types of activities. This condition that here I am mentioning essentially means the only activity that you are doing is adding a multiple of a row to another row. You are not doing the other guys. You are not, especially you are not doing exchange of two rows. That kind of upsets our stomach, if you will, a little bit. We are going to talk about that later. So in order to keep things simple, and really the condition that we are focusing on here is that we only employ, that's essentially the main thing that you do anyway, we only employ the elementary operation, which is add multiple of a row to another row. Let me just make sure that you guys remember. Suppose I have a matrix and it is A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. I ask, suppose I want to add three times second row to fourth row. So all such operation can be represented by matrix multiplication, and those matrices were very easy to organize, very easy to invert, and so on. So what is the matrix that does this? This kind of a matrices, we call them elementary matrices, E's, and they had a special format. So who is it that does this job? 3 times second row to the fourth row. We start with a diagonal, and what do we do with it? What changed? Say it again. We want to add 3 times of this row to that, and we just do that to the identity. So that is going to have an entry of 3 on the row that is going to be influenced on a column which matches the row number that you are picking. So the second row, that translates to, you wanted to take the second row and use that to modify the fourth row. The entry is going to be seated at a column that matches the row that you picked, and it's going to be on a row which matches the row that you are going to be influencing. Okay, so for example, if I take this matrix, multiply by that, what do I get? I say, well, the first 3, nothing is going to happen, so it's just as before. When I take this row, this is 0, 3, 0, 1, multiply by, say, this column, it's going to take 3E and M. So automatically adds triple of the second row to the fourth row, and down the line you go do the same thing to all of them. Now if I want to undo this, that is, take that matrix, bring it back to the original form that it had. So if I want to undo the damage, what do I do? Which is, I'm talking about the inverse of this matrix. If you want this to get it out of that, the inverse is very easy. The inverse is simply to undo the process. You multiply. So that matrix constitutes E inverse. Whatever E you had here, this was the E. Its inverse, in this case, obtained by just taking that number and turning into negative. Now, explanation of the magic later on is going to require to see how do these type of matrices multiply each other. If you have 2 matrices of this type, if you want to multiply them, a very simple rule is going to dictate how they actually multiply each other. That is 2 of these activities. Why do such a thing come up? Well, let's see. What do we do in Gaussian elimination? In Gaussian elimination, in the forward elimination step of it. You take some matrix, you act in some fashion on it. You add multiply a row to another row, and then multiply another row to another row, etc., etc. You keep doing these things. Now, suppose we have, we do one of these operations, and then say we do another operation, and then say we do another operation. Each of these operations that we perform is equivalent to one of these matrix multiplication. And suppose that's the only operation that's the only type of operation that we are doing. At the end, what do we achieve? When you do Gaussian elimination, what are you trying to get anyway? You're trying to get echelon form. You're trying to get these guys, turn them into zeros, and whatever is left here, that's fine with you. Well, if you achieve such a thing, and this is 0, and up here is some arbitrary bunch of numbers, what kind of a matrix is this thing anyway? According to the terminology that we introduced today, if the bottom is 0, and up here are just some random numbers, you call that what? That's just an upper triangular matrix. So the goal of Gaussian elimination in its first stage is to create an upper triangular matrix, and you can always do that. Now, I say, okay, this is light at the end of the tunnel. This is some sort of a factorization, really. If I manage to move this stuff to the other side, I really have A in terms of product of a bunch of other matrices on the right-hand side. That is really a type of factorization. Let's do one at a time. Let's try to get rid of these guys and throw them back to that side. Which one of these should I target to throw to the right-hand side first? Suppose I want to get rid of this entry here. Those other ones are kind of in the middle. I can't have access to them. How do I get rid of it? Like if in elementary mathematics, if you have 2x is equal to 5, how do you get rid of 2? Divide by 2, which now to introduce our notation, you multiply by the inverse of it. Is that right? The same as multiplying by half. So I want to multiply by the inverse of this. So that's going to be really E3 inverse times whatever I had. Well, if I multiply on this side, I have to multiply on the right-hand side as well. So what is E3 inverse E3? Just the identity, is that right? And identity times anything itself. So you have managed to get rid of one of these guys. It showed up on the right. Now what do you think I'm going to do next with E2? Okay, when I get rid of E2, in what place is it going to show up on other side of equation? So when I get rid of E2, I'm left with just E1. Where is E2 going to go? Here, in the middle, on the right, which one of them? Remember, matrix multiplication is not commutative. It's important for you to recognize the spot it's supposed to have. So when I get rid of this guy from the left, is it going to be here? Let's call it choice 1, choice 2, choice 3. Which one of them is it going to be? Well, let's carry it out. It looks like we are not sure of this thing. So let's multiply by this. When you multiply with the rest, you are taking E2 inverse, multiplying by that. So on the right-hand side, you have to do the same thing. You cannot move it around. So E2 inverse, E3 inverse, then U. So these two just, again, is identity. You are left with E1A. Right-hand side, you have E2 inverse, E3 inverse, then your upper triangular. Same question again. I want to get rid of E1. Now I have more places to worry about. Which one of them is it going to occupy on the front? Is that right? So A becomes E1 inverse, E2 inverse, E3 inverse, U. This is really what we mentioned in the previous lesson as well. If you have a bunch of matrices, you want to invert them. Not only each of them get inverted, but also the order in which they show up is going to be reversed. So here was 3, 2, 1. Over here is 1, 2, 3. So that's the price you pay for moving this to the right hand side. Now remember, each of these guys is a matrix inverse of an elementary matrix, just like this was the elementary matrix. Inverse of it is easy to get. The only thing that needs thinking is the multiplication of it. Well, let's postpone that portion later on. All that we realize right now is that these are a bunch of matrices. If you multiply them, you get some other matrix. It so turns out that the product of these matrices is going to be a lower triangular matrix. Not only that, you don't really have to slave over finding the product. It just comes to you naturally. There isn't any effort to be spent, and that's the very magic of it. So what we are saying is we are making a claim, and if you have time, we'll show it, that this is going to be unit lower triangular matrix of the type that we have talked about, L. It is such a thing. Moreover, it's easy to get. Simply, when you go through the Gaussian elimination, you are performing operations of this type. For example, add 3 times second row to the 4th row. You know that that matrix is represented by having a 3 here. You know that the inverse of it is having a -3 here. Now, if you just keep track of all of these numbers that you have used, just turn them into negative and put them in the right place as you go along with your Gaussian elimination. If you do that, that simple act of keeping and writing them in place, that would be equivalent to multiplying these elementary operations. Okay, let's go ahead and actually do it, and later we give an explanation of why does this magic work. Okay, let me just pick the exercise that is in the book. Here is some matrix A, 2, 8, 1, 1, 4, 13, 3, -1, -2, -5, -3, 3, -6, -18, -1, 1. Question: write LU factorization of given matrix. Okay, so what we want to do is to write A as L times U. Who is U? U is going to be the matrix that's going to be left out of this, that's going to survive this after you are done with the Gaussian elimination. This is going to be the upper triangular matrix left after echelon form is obtained. So we don't have that up front. We don't know what it is until everything is settled and all the dust is settled. L is going to be made out of, so this is going to be unit lower triangular matrix of this type. So it's ones here, that means it's a unit. Up here is going to be all zeros. Down here, the numbers that are going to sit in these places are the negative of multiples you have been using. So down here in its own respective place, it's going to be negative of multipliers used during elimination process. What do you mean by that? Well, let's go ahead and do. So I have this row 1, row 2, row 3, row 4. We said forward elimination consists of getting rid of these guys first. Well, how do you get rid of them? Let's you read it out to me. How do I get rid of 4? You say 2 row minus twice which row? Row 1 plus row 2. Is that right? You multiply this by minus 2. Add to that, you get rid of this guy. How do you get rid of minus 2? So let's call it 1 times row 1 added to row 3. Okay, remember we have a pivot. We are not going through this thing willy-nilly, doing whatever comes to our mind. We need to have a systematic approach so that you can program that, have a computer do it. Okay, minus 6, how to get rid of that? 3 times row 1 and then row 4. These are, of course, going to their own respective rows. So that tells me already what L is going to have. First of all, L is 4 by 4. Second, it's going to have 1s on the diagonal. Third, it's going to have zeros here. That's all fixed. Question is, who's going to occupy these spots? Negative of the numbers you are using to eliminate these entries go sit in the corresponding entries. So who's going to sit here? It's going to be 2. Who's going to sit here? Negative 1. Who's going to sit here? Negative 3. Is that right? Just these numbers that you are using to eliminate a certain element, negative of those are going to sit on exactly the same location. Is that clear to everyone? So the process is very simple. The question is, why does it work so nicely? Okay, well, after you do this, let's go ahead and do it. So you help me out doing this. So I have 2, 8, 1, 1. Minus twice that is added to this. So I get a 0. What do I get here? Minus twice the first row plus the second row. Negative 3. Does anybody see any mistakes or errors here or any questions? Okay, so help me out with the rest of it. What do I have here? 1. And what do I get for this? Minus 2 times negative 3. Okay, next entry better be 0. Well, 2 plus minus 2 is 0. Thank for that. Then 8 and minus 5. What does that give me? 3. 1 and minus 3. 1 and 3. Triple the first row, add to the fourth row. So that tripling and adding gives you a 0. Tripling 8, 24, and minus 18, I get minus 6. Excuse me, plus 6, is that right? Tripling that and adding to this one, I get 2. Tripling that and adding to this one, I get 4. If we have not made a mistake, let's just, it looks like we are on the right track. Okay, so these numbers sit in their respective places, except that the signs are switched. Why the signs switched? Because when you are taking the inverse, you remember negative comes, yeah, these matrices have to go to the right hand side and become inverses. Okay, the game repeats. The game repeats, and remember, our restriction was that the only operation we carry out is to add multiple of a row to another row. We are not doing anything else. Essentially, important thing, we are not multiplying, we are not exchanging any two rows. We don't have any pivot problems. We are not multiplying. We can always avoid that. So keep in mind, no exchanges. Let me write that here, like no exchange. This doesn't. Okay, that is not readable, so let's write it again. No exchange of rows. That's a crucial item. We are postponing that to later on for additional headache, but right now we don't need to deal with that. So when we have this matrix, what do we target? We target elements below the diagonal. We try to get rid of these entries. Again, no exchanges are needed. We are not worried about up there either. So how do I get rid of this entry? So I will have row 2, 1 row 2 added to row 3 is going to give me my new row 2. How do I get rid of 6? 2 row 2 and row 4 is going to give me this was row 3, this is row 4. While we have this thing fresh, let's just fill in the entries here. Who goes in this spot? -1. And who goes in this spot? -2. Okay, so the multiples that you use for eliminating these entries go sit in the corresponding location, except the numbers become negative. That negative reflects turning the inverse into its turning a matrix to its inverse. So if we go ahead and just do this, so we have 2, 8, 1, 1, 0, -3, 1, -3. Now you help me with this. What do I get? 0, 1 and -2 I'll have, -1, 3 and that is just 1. Last row, double that and add this, 0, 0. Doubling this, I make a 4. And doubling this and adding to that, I'll have a -2. Very good. So we are almost done with our echelon form. The only thing we got to get rid of is what? Row 4. This entry got to go. So how do I get rid of that? This is our pivot now. We don't touch those other guys, so we'll have 4 R3 plus R4 goes to our R4. While we have this thing in our mind, we enter for L. What do I enter for L here? -4. Once we have let's do this thing. So I'll have now 2, 8, 1, 1, 0, -3, 1, -3, 0, 0, -1, 1, 0, 0. And what do I have now? 0 and this entry 2. What kind of a matrix is that? No, what's the name? This is the upper, this is our U. This is the upper matrix. Who's the lower matrix? This guy that we create little by little out of the multipliers being made negative, that's our lower. So we write it here next to this guy. Say 1, 0, 0, 0, 2, 1, 0, 0, -1, -1, 1, 0, -3, -2, -4, 1. That is L, which is unit lower matrix. So by our design, these are all forced to be 1s. You have other options. What is the significance of this? What have we achieved? What we have achieved is that if you take this guy, multiply with this guy, you get your original. So that's a kind of record of Gaussian elimination. This is what our original was. This, I'm just copying our original. This is our A. So 4, 13, 3, -1 was -2, -5, -3, 3, -6, -18, -1, 1. Okay, so that wasn't that bad, huh? So we keep in mind, only one type of operation we use, which was adding multiple of a row to another row. We did not allow or have reason to exchange rows, and we can always stay away from multiplying a row by a number. The only operation, so let's emphasize one more round, only operation here, add multiple of a row to another. These multiples are negatives of multiple times a negative occupies the L matrix. Then you're all set. Okay, now to the justification. Why is this thing legitimate? Okay, you put these numbers here, perhaps you multiply and check that it all works, but what makes the magic to work so nicely? It has to do with the way those elementary matrices were. You remember these kind of matrices? What we want to say is that when you want to multiply two of these matrices, like one of them has a -3 in it and the other one maybe has a 7 in it, when you multiply them, all that happens is that this guy occupies its place, the other number occupies its place, and they just stay put, nothing else happens. Provided that your matrix multiplication follows a certain order as shows up in the steps of Gaussian elimination you use in creation of your echelon form. Let me just go ahead and show a couple of examples, perhaps. Let's see. So here, why does it work? Okay, so this is the explanation of the magic that makes it work. Let's take one of these matrices. Let's see. 1, 1, 1, 1. Okay, so anything I haven't written is supposed to be a 0. So if you want to see them, okay, help me out to multiply these things. Okay, so identity is not going to do anything here, so it's going to be 1, 0, 0, 0. This is a row of identity. You multiply, it just copies through. Okay, maybe a little bit faster. 0, 2, 1, 0, multiply. Yeah, this is doubling the second row, adding to the third row. What is the net effect of that? Well, add the double of the second row to the third row, what do you get? Now you multiply this, that's still identity. You multiply it by these guys, what do you get? The multiplication of these two entries, as if everybody holds his ground, just stays put there. Nothing else happens. Okay, that 2 is still here, and this 3 is still here. This magic works so long as this number is in a column that is to the left of this. If it was to the right of it, it would not work. Or two of them are in the same column. That still works. But if you write them in opposite order, the magic is not going to work, and that doesn't happen in our calculation either. So when you do Gaussian elimination, what do we do? What did we say we do? Let's see if I have it here. In Gaussian elimination, E3 is the kind of operation you carry out at the very end. At the very end, where are you worried about? What is your location? Let's see. In Gaussian elimination, to get the echelon form, you have this diagonal, and your first round of attack is on these entries here. These are first round, then next round, then next round. So like E3 is a kind of operation that you are doing here. E2 type of operation that you were doing there. When you are multiplying them in reverse, E3 inverse, the entry is seated at this location. E2 inverse, the entry is seated at one of these locations. When you multiply them, they just stay put. In the act of multiplication, all that happens is this kind of situation. That is like one of the last things that you were doing. In the reverse operation, the matrix associated with that shows up on the right. The one that you were doing earlier, it shows up on the left. When you multiply them, the numbers stay put. So that is a brief explanation why does this whole thing work. Now, well, what if you had to do permutation? That opens a big can of worms here that we have to handle. So next issue is, what if the steps of Gaussian elimination included permutation? In that case, we are not going to have a simple A is equal to LU. That doesn't work anymore, because in your process you swap things around. It doesn't work just that nicely. This does not work. We cannot guarantee that you can break it up into this type. What do you have instead? Well, you have to do certain permutations. If you take your matrix and rearrange all those rows that you want to rearrange down the line, then that final matrix does have a LU permutation. Now, during the process of Gaussian elimination, you might have gone through quite a few permutations. We can condense all of them inside one matrix and call that matrix a permutation matrix. So we let P is to be a permutation matrix. That would be responsible for all the row interchanges you are presumably going to do during that process. So if I take my matrix A and permute all the rows in it that I want to permute, then that final resulting matrix can be broken down to a lower triangular times an upper triangular matrix. Okay, and the process is going to be a little bit more involved. Maybe we wait for the next lecture on Monday. I'll take a couple of examples from here to see how that's going to be done, but let's wait on that. Let me ask you to from section 1.5, you want to do problems you choose from 1 through 8. And then on Monday we are going to have a lot more problems to look at. Okay, now before you go, you want to give me your homework, and Hopefully I'll have the result of your test back by Monday.